Welcome to this deep dive, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today we're undertaking a critical study of Einstein's photoelectric equation, energy quantum of radiation. It's a foundational concept in Unit 11. Dual nature of radiation and matter. And our mission, really, is to master this revolutionary idea, not just memorize it, to make sure you have complete conceptual clarity. So let's start with a really puzzling observation from daily life, something that, well, it forced physicists to rethink everything. You know how bright summer sunlight, which has that high-frequency ultraviolet light in it, can give you a pretty bad sunburn in just a few minutes?
Yes, of course. Everyone knows that. UV light is dangerous. It can cause chemical changes in the skin.
Right. Now, here's the paradox. Imagine a powerful industrial-grade red heat lamp. Let's say it's, 1,000 watts. Blindingly bright, just pouring out visible energy. You stand under it for hours. You feel very, very warm, but you will never get a sunburn. You'll never see any photoelectric effect whatsoever, no matter how long you stand there.
Wait, how can that be? The red lamp is so much brighter. It's delivering far more total power, more intensity per second than, faint UV light. If energy is carried by waves and the red lamp is delivering way more energy, shouldn't it eventually cause a bigger effect, like, damage or ejecting an electron?
And that is the absolute core of the mystery, the pre-quantum mystery. Classically, the effect should depend on the intensity, on the brightness. If you just keep pouring more energy into the system, you expect to eventually get there, right? To dislodge an electron. But here, the color, which is to say the frequency of the light, completely overrides the brightness. This counterintuitive reality is what forced the whole quantum concept, that light energy comes in individual discrete packets, and the effect is determined by the energy of one of those packets, not the total flow. Okay, so let's try to build a mental image for this. To resolve the paradox, we have to accept that light, at the moment it interacts with matter, is not a smooth, continuous wave, not something that spreads its energy out over time and space. Instead, you have to visualize light as a shower of discrete energy packets, like tiny bullets or little hammers. And we call these packets photons.
So the classical wave model, where energy is all spread out, it just fails completely here. We have to think only in terms of these particles.
Precisely. The crucial breakthrough is that the energy transfer is instantaneous, and it's absolute. One photon interacts with one electron. It's not a group effort. There's no waiting time, no accumulation. Now, for our main analogy, imagine you are an electron, and you're trying to escape from the surface of a metal. The binding forces of the surface create a kind of energy barrier, like a high fortress wall you have to jump over.
Okay, a wall.
Yes. And the height of this wall is the minimum energy you need to escape. Physicists call this the work function. We use the symbol phi0, or sometimes just W. To get over this wall, you need a high energy kick from a single photon. A single one. Now think about that red light photon. It has a low frequency, so it's like a soft tap. It really doesn't matter if a million of these soft taps hit you one after another. They never combine their energy.
So if the red light is super bright, that's just a massive number of soft taps, and none of them, on their own, can get the electron over the wall.
You've got it. Absolutely correct. The interaction is strictly one-to-one. Now contrast that with a single violet or a UV photon. High frequency. This is like a powerful high-energy hammer. It carries enough energy, in that one single packet to instantly punch the electron right over the wall.
And if there's any energy left over.
That's the crucial point. The electron uses the necessary energy, the work function, to escape. And any leftover energy, that becomes its kinetic energy. It's how fast the electron moves after it gets out. And the fact that this is instantaneous confirms there's no time for those weak photons to team up. So that mental picture of the one-to-one instantaneous collision is key. Now let's give this whole quantum idea the formal structure you'll need for your exams. Could you please read the insert's formal statement, the one defining the energy quantum in Einstein's famous equation?
Certainly, it says, radiation energy is built up of discrete units, the so-called quanta of energy of radiation. Each quantum of radiant energy has energy echo nu, where h is Planck's constant and nu the frequency of light. In photoelectric effect, an electron absorbs a quantum of energy of radiation. If this quantum of energy absorbed exceeds the minimum energy needed for the electron to escape from the metal surface, work function phi0, the electron is emitted with maximum kinetic energy. Kmax equals h nu minus phi0.
Excellent. That final equation, Kmax equals h nu minus phi0. That is Einstein's photoelectric equation. It's probably the single most important relationship in this entire unit. Let's just break down how it's really just the law of conservation of energy applied to our one-to-one interaction.
Yeah.
Step one. What's the total energy input? It's the photon's energy, right? E equals h nu. And remember, this energy depends only on the frequency, nu, and that universal constant h, not on intensity.
Okay, so step 2 must be the cost, right? The energy the electron has to pay to escape. The work function, phi naught.
Precisely. That cost, phi naught, is paid to the metal to break free. So step 3, the law of energy conservation tells us that the input energy must equal the cost plus any excess energy the electron carries away. So we get this fundamental energy balance. 8 nu equals phi naught plus K max.
And if you just rearrange that, you get the insert equation, K max equals h nu minus phi naught.
Exactly. And that one single statement explains everything that classical physics couldn't.
So, if the input energy, h nu, is less than the barrier energy phi naught, the equation would give a negative K max.
Which is impossible. Kinetic energy can't be negative.
Exactly. It can't be negative. So that means emission is physically impossible if the frequency is too low. That point where Kmax is exactly 0, where the electron just barely scrapes over the wall with no leftover speed, that defines what we call the threshold frequency. We call it nu naught.
So there's a minimum frequency needed for anything to happen at all.
Precisely. The condition is that h nu must be greater than or equal to phi naught. And from that, we get that the threshold frequency, nu naught, is just phi naught divided by h. Frequency is the gatekeeper. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAMSAM.com. Now let's just confirm this with a quick numerical check. This kind of calculation is really essential for your exams. We'll use a standard example. Sodium metal. It has a work function, phi naught, of 2.3 electron volts, and we shine green light on it with a frequency of, say, 6 times 10 to the power of 14 hertz. So we need to check if the energy of one green photon, h nu, is bigger than the 2.3 eV barrier.
Exactly. First, we calculate the photon's energy, E equals h nu. And if we convert the units from joules to electron volts, which is just more convenient here, that single green photon has an energy of about 2.48 electron volts. So we have an input energy of 2.48 eV hitting a barrier of 2.3 eV. What's the maximum kinetic energy?
Well, the input, 2.48, is greater than the barrier, 2.3, so emission definitely happens. And the kinetic energy, Kmax, would just be the difference. So 2.48 minus 2.3 is 0.18 electron volts.
Perfect calculation. And that 0.18 eV determines the fastest possible speed of the ejected electrons. In a lab, we'd measure this using something called the stopping potential, V naught. Since E times V naught equals Kmax, we'd need a negative voltage of 0.18 volts to just stop those fastest electrons.
And this kinetic energy is fixed no matter how bright the green light is.
Yes, and that's the experimental proof. Now, here is where it gets really, really interesting. This connects this quantum concept to, well, the entire structure of modern physics. The photoelectric effect confirmed that light, which we knew was a wave from experiments like interference and diffraction,
Right.
must also sometimes act like a particle, the photon.
This whole wave-particle duality thing for light, that must have been a huge shock to physicists back then.
It was profoundly shocking. It meant our basic concepts were incomplete. But it led to this deep realization about symmetry in nature. A physicist named Louis de Broglie looked at what Einstein had done, and he asked a very powerful symmetric question. He said, if light, which we think of as a wave, can act like a particle,
Then could matter,
Yeah.
which if we think of as particles like electrons, could they also act like waves?
precisely. The photoelectric effect was the logical step that led directly to the de Broglie hypothesis that matter has a wavelength. It's the central idea of this whole unit, really, that everything has both a wave nature and a particle nature. Okay, now let's address the silent killers. The two most common misconceptions that can tragically steal marks in your exams. First, wrong idea. Thinking that if you just wait long enough or use incredibly intense light, you could eventually build up enough energy to kick an electron out, even if the frequency is below the threshold.
I can see why students would think that. It's the classical intuition, isn't it? Just keep adding energy until you have enough.
It is, but the correct idea is that the photon-electron interaction is all or nothing. If a single photon doesn't have enough energy to get over that phi naught barrier instantly,
It fails.
it fails. The electron immediately gets rid of that little bit of energy, usually as heat. It can't store it and wait for the next photon to arrive. So remember this hook. Frequency is the gate, intensity is the flow. If the gate is locked because the frequency is too low, no amount of flow can get through.
Okay, so frequency is the gate. Got it.
Second wrong idea, that increasing the intensity of the light, say making the UV light brighter, will increase the maximum kinetic energy, the Kmax, of the electrons.
So making the light brighter doesn't make the electrons fly out faster? That feels wrong.
It feels wrong, but it's a common intuition error. You're mixing up quantity and quality. The correct idea is that Kmax is determined only by the energy of the individual photon, h nu, and the work function. Kmax depends on the color, not the brightness.
So brighter light means more photons, so
Yeah.
more electrons get ejected, but each one has the same maximum speed as before.
Precisely. Brighter light increases the photocurrent, the number of electrons per second. But it doesn't change the energy any individual electron receives. To really lock this concept in your memory, let's use the equation itself as a mnemonic. H nu equals W plus KE. Just keep saying that. It's the energy accounting rule.
Photon gives work plus kinetic energy.
Perfect. Or, for a memorable phrase, how about this? Frequency funds the escape. Intensity funds the crowd. One photon, one electron, one quantum leap.
I like that. It emphasizes the one-to-one nature of it.
And finally, a physical gesture. Hold one hand up high. That's your input energy, H nu. Now bring your other hand up to your chest. That's the barrier, the work function, the gap between your hands that then moves forward quickly. That's the kinetic energy, the instantaneous escape. If your high hand can't clear the chest barrier, there's no forward motion. Nothing happens. Okay, so to summarize this entire deep dive, here are 3 essential exam-safe factual points that capture the energy quantum of radiation. First, light energy is made of discrete packets called photons, and each one carries an energy E equals h nu. The photoelectric effect is the result of a single instantaneous collision, one photon, one electron. Second, Einstein's equation Kmax equals h nu minus phi naught is just a statement of energy conservation. The photon's energy input is split between the work needed to escape and the kinetic energy of the electron. And third, a minimum threshold frequency nu naught is absolutely required for emission. Below this frequency, nothing happens, no matter how intense the light is, because the individual photons just don't have enough energy. To get maximum conceptual clarity and marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes, ProfSam.com. Study hard and keep that curiosity alive. All the best.